This is number 4 on the optimization worksheet. There was a mistake in the first video, and so I'm redoing it to try to correct that error. So this is just going to have number 4. The second video has the rest of the problem. So it says a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs $10 per square meter, and material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. So, this is a rectangular solid without a lid. So, the volume of a rectangular solid is equal to length times width times height, but I'm going to choose to call my length, width, and height X, Y, and Z. That's just what I want to do. So this is going to be my X, and this is going to be my Y, and this is going to be my Z. So X is how wide this part is, and Y is how long this part is, and Z is how tall the box is, the height. Okay, so volume in general is equal to length times width times height, and they said in this problem it has to be 10 cubic meters. So that is the constraint equation in this problem. And so now we want to optimize a certain equation. We have to figure out what that is. In the last sentence there says to find the cost of materials such that it for the cheapest container. So that means we have to come up with the cost equation, and we want it to be the cheapest, so we want to minimize that equation. So the cost of the materials is going to be the surface area, right? That's what you construct the box out of. So the base has the dimensions X times Y. So the cost will be the base, and there's only one of those, times $10. So that is going to be the cost of the base. Okay, and then let's see, let's do the front panels, and then we'll do the side panels. Oops, side. Right, so there's 2 front panels, so there's 2 of them, and then we'll say the dimensions are X times Z, and then it says it's $6 per cost there, and then the sides are Y by Z, and there's 2 of those, to Y times Z, and those are also $6. So this is our cost equation, and that's what we want to minimize. So what we have left to do is to write everybody in terms of one variable if we can, and we can, and then we want to find the value of the variable, and I'm going to write everybody in terms of X. So I'm going to find the value of X that will minimize the cost equation so that I'm spending the least amount of money. And I still am meeting my constraint of 10 cubic meters for my volume. So let's begin with this. First, I want to call my volume not length times width times height, but X times Y times Z. Okay, and then they said something at the beginning of this problem. They said the length of its base is twice the width. So I can choose to name this length and this, or this length, it doesn't matter. I want everybody in terms of X, so I'm going to say that this is the width, and the width is twice the length. So that's how I'm going to choose to write Y is equal to 2X using that piece of information. So that means I can go in here and rewrite every Y. I'm going to replace every Y with 2X. And then I can also, if I do that, let's do it up here. Y is 2X. I can rewrite Z in terms of X. So this is 2X squared times Z is 10. So I can solve for Z here and get 10 divided by 2x squared, or 5 over x squared. And that's going to go in for my z's. All right, so right here, my cost equation, I want to write it all in terms of x. So the cost in terms of x is going to be x times y, which is 2x, times $10, plus 2 times x, times 6, so let's go ahead and make that 12, times z, which is 5 over x squared, plus 2 times 6, which is 12, times y, which is 2x, times z, which is 5 over x squared. So now we have our cost equation all in terms of one variable, so that's very helpful. Now we'll just multiply this all together, so we get c of x 2 times 10 is 20 times x is 20 x squared plus 12 times 5 is 60. And then we have an x divided by x squared. This is x to the negative 1. And then we have 10 times 12, which is 120. We have an x divided by x squared, which is x to the negative 1. Okay? So now these are like terms that can be combined. Let's combine those guys. We get the cost equation is equal to 20 x squared plus 180 x to the negative 1. All right. All of that was just cleaning up my cost equation. Now I'm going to do the calculus. Let's take the derivative and let's do find the critical value and see if it's a minimum. So the derivative here, c prime of x, is going to be 40 x minus 180 x to the negative 1. And to find the critical value, I'll set that equal to 0 and solve. So let me move up here. We'll say that 40 x is equal to 180 over x. So I did two things when I moved from here to here. I added 180 x to the negative 1 to the right side, and then I rewrote my negative exponent as a positive exponent. The reason I did that is because I have a fraction equals a fraction, and I want to solve this by cross multiplying. So 1 times 180 is 180, and 40x times x is 40x squared. So let me see. Yep, I could feel it. I made a little mistake. So let me correct this. This is going to be, no, that's okay. What is not okay? Oh, this is not okay. Negative 180 x to the negative 2. That is a mistake. So let me fix that. I don't know why. What is up with all these mistakes? Okay. So I get 40x is equal to 180 over x squared. That should have happened. So x times x squared is x cubed. 1 times 180. So now this is going to be x cubed is equal to 180 over 40, which 10 can go out of that, and that will be a 9 over 2. X cubed is 9 over 2, and when you take the cube root of this is about equal to 1.65 centimeters. That's what that is about equal to. Let me see if I'm okay with that. I'm okay with that. Let us do our little test value. 1.65. Let's pick something to the left of that, maybe 1, and something to the right of it, maybe 2. And we'll plug it in our derivative, which is right here. So this is really 40x minus 180 over x squared. So this is our derivative. So what we're checking is to see if we get a positive or a negative. When I put in 1, I'll have 40 times 1 minus 180 divided by 1, which is a negative number, which says that this side of that number is decreasing. When I put in 2, I'll have 40 times 2, which is 80, minus 180 divided by 2 squared is 4. 180 divided by 4, which is 4, do I have my calculator that'll go in? 16, 20, 45. This is minus 45. So this is a positive over here, so this is increasing. So this value right here gives us a minimum. That's nice, okay? So that tells me that x for this situation should be 1.65 centimeters. I can say y is equal to 2 times x, and that should be 3.30. I'm sorry, not centimeters, meters. What is going on today? Meters. And then z should be 5 over x squared, which ends up being 1.84 meters. And so what will the volume be? You can check that it's going to be 10 cubic meters. You multiply this times this and this, length times width times height, and you'll get 10 cubic meters. What will the cost, the minimum cost be? This is the derivative, but right up here is the cost equation. So you can plug it in here and say, well, what will it cost? If x is 1.65, this is 20 times 1.65 squared plus 180 divided by 1.65. And when you plug that in, you get that your minimal cost will be 163, 54 cents. All right, so that's our minimal cost. That's number 4, and that's better.